We're going to be starting chapter 6, which is ultimately on electron configurations, meaning where are the electrons. Well, to get started, we're going to learn about light and some of the equations that are related to light, because light is one of the ways that we have learned about the electrons and their energy levels and allowed positions and a few other things of that nature. So that's why we're going to begin the chapter with talking about light. We'll talk about the wave nature and about the particle nature of light. We'll briefly review what an atomic spectrum is, and then we're going to start with the simplest of all atoms, which would be a hydrogen atom, because we only have one electron that we have to deal with. And we'll then quickly get into more complex atoms, and when we're getting into more complex atoms, meaning more electrons, then we'll be dealing with and we'll be learning about quantum numbers. We have quantum numbers that represent essentially how big an atom is. So when we talk about energy levels or sublevels, we'll talk about essentially different paths that electrons can travel in within a given shell. And then we'll also be learning about orbitals. So these are several terms we have to be learning throughout this conversation here. Ultimately, we are working towards electron configurations or electron arrangements, and we'll learn those electron arrangements and configurations in relationship to these quantum numbers. Okay, I think we'll just go ahead and get started, and let's begin with our normal review. And our first question asks, a sample of an unknown hydrocarbon is placed in a 1-liter container and vaporized by heating to 90 degrees C at 1.524 atmospheres. The vapor filling the flask at this temperature and pressure weighs 8.587 grams. Calculate the molar mass of this hydrocarbon. Okay, we're after the molar mass of a gas, and we use our units for that. And so, step 1, the molar mass would be grams per mole. Since this is a gas, for step 2, we're going to start with our big denominator line. So it's a little bit different from our normal step 2. And now, where do we get the unit of grams from? And that would be the mass that was actually given. And then where do we get the unit of moles from? Well, that would be from the universal gas constant with moles in the denominator. That then tells us where the other 3 variables go. The temperature in kelvins on the top, the volume in liters, and the pressure in atmospheres goes on the bottom. And let's go ahead and plug in these values. And once we plug them in, then I would go back and scratch out all those units that canceled, circle what's left, and we should see we have grams and moles left, which gives us confidence that we set this up correctly. When I put this on my calculator, I come up with 168 grams per mole. Does that answer seem reasonable? Yes, it does. What would seem not reasonable? Maybe 1,600 grams per mole, or 1.68 grams per mole. Again, sometimes numbers being very large or very small tell us we've made a mistake. Okay, next we're asked to calculate the density of argon at 22 degrees C and 0.851 atmospheres. At first glance, we may think that we weren't given enough information for this, but the reason for that is one of our pieces of information comes from the periodic table. Again, we are using our units, and that begins with the density of a gas would be grams per liter, so there's step 1. And then again, we're dealing with gas law information, and so for step 2, we're going to start with our big denominator line. And then where do we get grams? Well, that's actually from the molar mass of argon, and from the periodic table I get 39.95 grams per mole. And where do I get liters? From the universal gas constant with liters in the denominator. No, moles is already canceled. And now my temperature in kelvins needs to go on the bottom, and my pressure in atmospheres goes on the top. When I plug these numbers in, and then scratch out all those units, I see I'm left with grams per liter. It's always a good idea to scratch out those units that cancel and circle what's left, so that when we are done with step 3, we know we've done it correctly. Okay, and putting this on my calculator, I come up with 1.40 grams per liter. Does this answer seem to make sense? And it seems reasonable. Next, ammonia is produced by the reaction between hydrogen and nitrogen. And we're asked how many liters of ammonia at 350 kelvins and 2.11 atmospheres can be produced when 67.5 liters of nitrogen at STP react with 181 liters of hydrogen at 398 kelvins and 6.12 atmospheres. Okay, a lot of information is given in this problem, but do note they're asked about the amount of product, and they give us the amounts of both reactants, so that tells us this is a limiting reactant problem. Now, we're after the amount of ammonia in liters, and we're going to be using our units for that. So step one, we're after liters of ammonia. Always start with your primary equation, which is what gets you to the answer you're after. And then, being gas law information, we're going to start with our big denominator line. And now where do we get liters? From the universal gas constant with liters in the numerator. And that tells us where everybody else needs to go. And do we have moles of ammonia? No, that's why we're given that other information on the other reactants. So we're going to use that information on nitrogen and hydrogen to determine the number of moles of ammonia, starting with the amount of nitrogen, or give me the information from nitrogen, and this is at STP, so we can use our normal step 2, where we start with that 67.5 liters of nitrogen, and then go from liters of nitrogen directly to moles of nitrogen. And again, we can only do this because it's at STP. Any other temperature and pressure, we'd have to do it the long way with a big denominator line. Okay, that gives us moles of nitrogen, so we're not after that. Can we go from moles of nitrogen to moles of ammonia? Yes, we can from our balanced chemical equation. And I hope you remember the molar volume of a gas at STP, 22.4 liters per each mole. And then the balanced equation says 2 moles of ammonia formed from 1 mole of nitrogen. And this says that I can potentially form 6.027 moles of ammonia from the nitrogen. Okay, now for the hydrogen. We're after moles of ammonia still, but we're starting with a gas, so under normal gas conditions, and so we start step 2 with the big denominator line. And then we get moles of ammonia from moles of hydrogen, so we start with our universal gas constant with moles in the numerator. And that tells us where everybody else ends up going to canceling. Here's that volume in liters, the pressure in atmospheres, and the temperature in kelvins. Now again, that does give me moles of hydrogen. That's why I labeled it H2, just to remind us it's not moles of ammonia. To get moles of ammonia out of moles of hydrogen and into moles of ammonia, using the coefficients from the balanced chemical equation. And so we can form potentially 22.6 moles of ammonia from the given hydrogen. Okay, so how much can we actually form? The smaller amount. The nitrogen was the limiting reactant. It limits me to the maximum amount of ammonia that can be formed. And now that I have the number of moles of ammonia, I can plug that into my original equation. And when I put this all on my calculator, I come up with 82.1 liters. Does that answer make sense? Well, let's see. Since it was limited by the nitrogen, and that was at 67.5 liters, 82.1 seems reasonable. Now, if it was in the hundreds or thousands, that might seem a little unreasonable. We're told a sample of a smokestack emission was collected into a 1.25 liter container at 752 torr and analyzed. The analysis showed 92% carbon dioxide, 3.6% nitrogen monoxide, 1.2% sulfur dioxide, and 4.1% water by mass. What is the partial pressure of each gas? Well, our primary equation is the partial pressure of each gas is equal to its mole fraction times the total pressure. And it would be nice if they gave us the mole fraction, but they didn't. They gave us the mass fraction. So we're going to have to do quite a bit of side work to come up with what we need. First, the number of moles of carbon dioxide. Well, we take that 92% and turn that into 92 grams of carbon dioxide. Molar mass of carbon dioxide is 44.0 grams per each mole. So that 92 grams is 2.09 moles of carbon dioxide. Okay, well that gives me the number of moles of carbon dioxide, and my mole fraction would be the moles of carbon dioxide divided by the total number of moles. So it looks like I need to take the masses of the other reactants or the other species and get their number of moles as well. So the 3.6 grams of nitrogen monoxide for 0.120 moles, the 1.2 grams of sulfur dioxide for 0.0187 moles, and 4.1 grams of water at 0.228 moles of water. Putting this, or adding these all together, I come up with a total number of moles of 2.46. And now the mole fraction of carbon dioxide would be equal to that 2.09 moles of CO2 divided by the 2.46 total number of moles of gas times the total pressure of 752 torr or 640 torr. Now that we've done all that side work, the rest of our calculations should go easier. The partial pressure of nitrogen monoxide is equal to its mole fraction times the total pressure. So its number of moles divided by the total number of moles times the total pressure. Same with the partial pressure of the sulfur dioxide, its mole fraction, so its number of moles divided by the total number of moles times the total pressure. And lastly, water has its mole fraction, which is its number of moles divided by the total number of moles times the total pressure. Okay, an unknown gas diffuses 2.828 times faster than oxygen at the same temperature and pressure. Identify this gas. Well, our primary equation is the molar mass of our unknown over the molar mass of O2 to the square root is equal to the rate of the O2 to the rate of the unknown. And now, where does that 2.828 go? Well, this gas diffuses faster than the oxygen, so that's going to go with the rate of the unknown. So let me go ahead and take the molar mass of the unknown over the molar mass of the O2. And let's go ahead and square that so that we get rid of the square root. Is equal to the square of 1 over that 2.828. Let's multiply out the molar mass of O2. And here's the molar mass of the unknown isolated. Let's plug in the molar mass of O2 and square that 1 over 2.828. And I get 1/8 of 32 grams per mole, or 4 grams per mole. And we're asked to identify this gas. Only one gas has this molar mass, and of course that's helium. Okay, what is the average velocity of nitrogen molecules in the atmosphere at room temperature? Okay, we're going to use our original velocity equation. The velocity of the gas squared is equal to 3RT over the molar mass of the gas. Let's square root both sides to get the velocity by itself. And the version of R, the universal gas constant for this, would be 8.31 times 10 to the third gram meter squared per second squared over mole kelvins. It normally shows up at 8.31 joules per mole Kelvin, but a joule would be 10 to the third gram meter squared per second squared. And actually we have all the information, so let's go ahead and plug it in. putting this all on my calculator. Now do note, the grams and moles cancel, the kelvins cancel, leaving us with meters squared per second squared, which when I take the square root, gives me the appropriate units of meters per second. So even though we didn't use our units to set up the problem, they're still there to help us make sure we're not making any simple mistakes. Does our answer make sense? And it's hard to really say because it's hard to relate to the velocity of gases, but as I mentioned before, gases are traveling at tremendous speeds, and a little over half a kilometer a second is a tremendous speed. Okay, at what temperature will the average velocity of nitrogen molecules be twice their average velocity at room temperature? Okay, the equation that relates temperature to velocity is equal, it would be the ratio of your temperature at temperature 2 over temperature 1 square rooted is equal to your velocity ratio of your gas at those two temperatures. Let's square both sides and then multiply out T1, and here's T2, our new temperature isolated. Now we weren't actually given the actual velocity, but we were asked about doubling the velocity. So essentially that velocity ratio is going to be 2. 2 squared is 4. 4 times the 295 says that at 1180 kelvins, these gas molecules would be traveling at twice their velocity at room temperature. Okay, on to new material, and we're going to be working towards understanding electron configurations, which is where are the electrons, what are they doing, and this is actually important. Let me just kind of take a time out here and point out that all chemical reactions are about electrons. So elements are either trying to gain electrons or lose electrons. If they weren't, then chemical reactions wouldn't occur. Elements react because they're trying to change their number of electrons. So it's very important for us to understand where those electrons are so that we can understand why they're trying to change the number that they have. Now I would point out how many electrons an element has is based on the number of protons the element has, and that's why ultimately what makes one element different from the next is the number of protons. But a neutral atom would have a specific number of electrons corresponding to that number of protons. And we'll learn by the end of this chapter why elements are trying to change their number of electrons and what they're trying to change those numbers to. Okay, to understand the electron configurations, we're going to first start with learning about light, because this is what allowed us to measure the characteristics of electrons. So let's go ahead and learn about light, and first we're going to learn about the wave nature of light. And so like any wave, we can describe this wave in terms of the wavelength and the frequency, where the wavelength is represented by the Greek letter lambda, and the wavelength would be essentially the length of a wave, so the distance between two troughs or two peaks or two points that are at an identical place in two successive waves. So we see in this illustration the wavelength, and we're not going to talk about amplitude. You might talk about that in a physics class, but amplitude isn't going to show up for us. But do note the difference between these two waves. We have a longer wavelength at the top, and so it has a lower frequency. Since it has a longer wavelength, it's going to take longer for them to go by, so a lower frequency of them going by. And the shorter wavelengths in the picture below essentially has a higher frequency, because if they're traveling at the same speed, more of these waves are going to go by in a given point, in a given amount of time. Okay, so again, the other variable is the frequency, represented by the Greek letter mu, and this is again how many waves go by in a given point of time. And so they would have units of reciprocal time, like so many per second, so many per minute. Actually, it's always going to be per second. Now this illustrates the electromagnetic spectrum, and so it's a long, large variance in different wavelengths. Over to the left we have the short wavelengths, over on the right we have the long wavelengths. So radio waves are very long. Then microwaves are a bit shorter. Then we have the infrared, which are getting shorter yet. And then we have a tiny little portion of the visible light spectrum. Then going to shorter wavelengths, which by the way have higher energy, we have the ultraviolet spectrum, then moving into X-rays, and then finally into gamma rays. And so on the left we have the highest energy photons, and we'll be talking about energy here in a little bit. But I would point out essentially short wavelengths on the left, long wavelengths on the right, and the shorter wavelengths have the greater amount of energy. And the ones with the greater amount of energy, the ones that are more dangerous for us because they can break chemical bonds. And so when we look at the right, microwaves, radio waves, infrared, they're not going to have enough energy to break chemical bonds. So we don't need to be worrying about them essentially breaking our bonds. Okay, I did mention that frequency was the number of waves that would go by in a given amount of time, and so they have units of reciprocal time, so reciprocal seconds. And by the way, the unit of hertz is a reciprocal second. So in our example, if we have a frequency of 100 million reciprocal seconds, that means we have a frequency of 100 million hertz. Now, the wavelength times the frequency is equal to the speed of that wave. And this would be true for any wave. The wavelength times the frequency is equal to the speed. Now, since we're talking about light, we're talking about the speed of light, and the speed of light is constant in a vacuum. I have to say that, in a vacuum. If light is going through water or glass, it actually slows down a little bit. We're not going to worry about that. We're always going to be using that 2.998 times 10 to the 8th meters per second. And so do note, since the speed of light is constant, if we know the frequency, we can calculate the wavelength, or if we know the wavelength, we can calculate the frequency. In other words, if you're given one, you can always calculate the other. Let's look at an example. We're asked what is the frequency of a photon with a wavelength of 589 nanometers. Okay, well, our primary equation, lambda nu, is equal to c. And we're after the frequency, so let's divide out lambda, the wavelength, and here's nu, the frequency isolated. We have the speed of light at 2.998 times 10 to the 8th meters per second. We have the wavelength. Do note that's in nanometers, so I have to convert that into meters so that those units cancel. And now we can see that those units of meters cancel, giving us the appropriate unit of reciprocal seconds at 5.090 times 10 to the 14th reciprocal seconds. We expect the frequency to be very high. Now that really depends on what the wavelength is, of course. But most visible wavelengths are going to have wavelengths in the region of hundreds of nanometers and frequencies in this range of 10 to the 14th-ish reciprocal seconds. Okay, light also acts as a particle, meaning it actually has an energy associated with it. And the equation here is the energy of light is equal to h nu, where h is Planck's constant and has a value of 6.626 times 10 to the negative 34 joule seconds. Now I always remember the equation E equals h nu, but very often we're given wavelength, so if you want to also remember E is equal to hc over lambda, which of course is essentially E equals h nu, or nu solved for in terms of lambda, there is that variance. But for me, I mainly remember E equals h nu. Okay, let's take a little bit of time to talk about atomic spectra, which is essentially the spectrum of light that's emitted by a specific element. Now, these wavelengths are emitted, and all light comes from electrons transitioning from a higher energy state down to a lower energy state. So again, if light is being absorbed, then the electrons are going from a lower energy state to a higher energy state, but if light is being emitted, the electrons are going from that higher energy state to the lower energy state. So this is where the energy of light is coming from. So here we see an illustration of the wavelengths of sodium, hydrogen, and mercury, and we see these discrete bands. And these discrete bands are representative of the allowed transitions of electrons, where they're going from a higher energy state to a lower energy state. And so these bands represent the energy difference between two allowed states. Now we don't have a continuum for an individual element, because there are just allowed states that the electrons can be found in. And we'll talk about that more in a little bit. But I will also finish by saying, note that these are quite a bit different, and so we can use the atomic spectra to identify what element is present. Okay, another example, we're asked to calculate the energy from the yellow line in the sodium spectrum, where the wavelength is 589 nanometers. And we want our answer in joules per photon, which is the way it's going to come out using Planck's constant. Okay, well, our primary equation, E equals h nu. Sometimes we see delta E to remind us this is actually a change in energy between the higher and lower energy state. Meaning from the energy state of the higher electron to the lower allowed orbitals. And we're after the energy, so it's already set up, and Planck's constant is essentially going to be given to us. Now, nu, we don't have, we're given lambda, so we're going to set up a secondary equation to calculate nu from lambda, where nu is equal to the speed of light divided by lambda. We always have the speed of light, and lambda was given in the problem. Once again, we have to convert that from nanometers into meters. And this gives me 5.090 times 10 to the 14th reciprocal seconds. I'm going to go ahead and plug that into my original equation along with Planck's constant. Now, I've always felt that Planck's constant should actually have the units of joules seconds per photon, because when we multiply that by the frequency, we actually are given that that energy in joules per an individual photon. So again, using E equals h nu, we're always going to get our answer in joules, but it really is joules per photon. Now, we might instead be asked to calculate this energy in joules, in kilojoules per mole of photons. This is a common unit of energy when we're talking about light. Kilojoules per moles of photons. Okay, well, what are we going to do? Well, we're going to use our units for this, and so our normal step 1, we're after kilojoules per mole of photons. Then step 2, we're going to take the just calculated energy in joules per photon. And now step 3, let's get out of joules. Can we go straight to kilojoules? Of course, that's a simple metric conversion. And then let's get out of photons. Can we go to moles of photons? Yes, we sure can, using Avogadro's number. Okay, base 10 number, still going with the base unit, 10 to the 3rd joules per kilojoule. And then Avogadro's number of entities per mole of entities. So that's 6.022 times 10 to the 23rd photons per mole of photons. And that gives us 203.1 kilojoules per mole. So when we have photons that are near the visible spectrum, which again is going to be in hundreds of nanometers, then expect your energy in hundreds of kilojoules per mole. Now remember, if your photons get smaller by a factor, the wavelengths get smaller by a factor of 10, then your energy is going to go up by a factor of 10. If they get longer by a factor of 10, then their energy is going to go down by a factor of 10. But again, visible light, so in the hundreds of nanometers in length, is going to produce an answer in hundreds of kilojoules per mole. Now this calculation actually tells us something very important, and that is that there is a difference between two energy levels in the sodium atom that actually differ by that 3.373 times 10 to the negative 19th joules. So again, we have this difference in energy between two allowed energy states. And now let's talk about the hydrogen atom, where we want to now see the relationship between energy and electrons. Now the hydrogen atom allows us to start with a nice, simple, clean picture where we have just one electron. If we bring in more electrons, it's going to really muddy the picture real quick. So that's why we want to start with a nice, easy model. Now Niels Bohr did some groundbreaking work at the beginning of the 20th century, where he determined that the relationship between the energy of an electron and its principal quantum number, that's what that N is, the principal quantum number, which is essentially the allowed energy state based on how far the electron is from the nucleus. Actually, it's going to be a whole number, and do note we can see N equals 1, 2, 3, so essentially think of this as shells of electrons, or shells of allowed positions electrons can be around the atom. And so when N equals 1, we have an interior shell. So think of a circle where this is the innermost shell that the electrons can be found in. When N equals 2, well, now that shell's gotten bigger. N equals 3 has gotten bigger yet. So essentially imagine as you go to N to 1, to 2, to 3, to 4, etc., you're getting bigger and bigger and bigger and bigger. Okay, that R sub h is the Rydberg constant, and we'll be given that for the calculations when we need it. And do note that it has the units of joules. Now, sometimes we are interested in the absolute energy of an electron, and this is the equation that we would use for this. Let me go over some terms. We have the ground state, which would be the lowest energy state available, and this is always when N is equal to 1 for the hydrogen atom. Any state above this is called an excited state, so when N equals 2, 3, etc., then we have an excited state. And now photons are going to be liberated or released when an excited electron falls back down to a lower state. So if an electron goes from N equals 3 down to N equals 1, it's going to release a photon of energy that matches the difference in energy between those two states. So delta E, our change in energy, is equal to h nu, and so this is how we can calculate the energy of that energy transition. And I would remind you that the energy is transitioning from N high to N low. So when the electron is in an outer excited state, going down to a lower energy state. Maybe not necessarily N equals 1, it could be N4 going down to N2. Now in high, it's going to be E high is going to be where N is high, and E low is when N is low. And so we can take Niels Bohr equation and essentially rearrange it in this respect. And this is the more practical version. And so the more common primary equation when we're calculating the energy of a photon and a hydrogen atom, where the change in energy between our two states is equal to the negative Rydberg constant times 1 over N high squared minus 1 over N low squared. We'll be using this equation quite a bit, so remember that equation. And actually remember all these equations. Lambda nu equals C, and E equals h nu, and so this will be our third primary equation. Okay, let's look at an example to see what we might be doing with this. We're asked what wavelength of light is emitted when a hydrogen electron moves from the third principal shell to the second principal shell. Well, the third principal shells were N equals 3, the second principal shells were N equals 2. Okay, what wavelength of light? Well, we only have one equation with wavelength, and that's lambda nu is equal to C. Let's solve for lambda. Do we have nu? No, we're going to get that from the energy equation, where E, or delta E, is equal to h nu. Let's solve for nu. And we're missing change in energy, which comes from Bohr's equation, where delta E is equal to negative R sub H, the Rydberg constant, times 1 over n high squared minus 1 over n low squared. And again, you will be provided with the Rydberg constant, and you need to recognize n high was where we had n equal to 3, and n low is where n is equal to 2. Now do note 1 over 9 minus 1 over 4 gives us a negative number, so that when we multiply that by that 2.180 times 10 to the negative 18 joules, we get a positive energy. If you had a negative energy at this point, you would come up with a negative wavelength. Now there is such a thing as negative energy, but we'll talk about that another time. But there is no such thing as a negative wavelength. Okay, let's go ahead and plug in our change in energy along with Planck's constant. And do note how those two joules cancel to give us the appropriate unit of reciprocal seconds. So again, even though our units aren't setting up our problems for us when we're using equations, they still need to be paid attention to so that they could help make sure that we might catch simple mistakes. And they should always work out to give us the units that we should be getting. And so when I plug in the speed of light, and divide that by the frequency which we just calculated, note how the reciprocal seconds cancel in both to give us the appropriate unit of meters. At 6.560 times 10 to the negative 7th meters. And I convert that into nanometers, I get 656.0 nanometers. Remember, 1 nanometer per 10 to the negative 9th meters. So we're ultimately dividing that wavelength in meters by 10 to the negative 9th meters underneath 1 nanometer. Let's ask, does our answer make sense? Well, this is matching a visible light wavelength, so I'm going to go with yes, this does make sense. And again, if I had a negative value, I've made a mistake somewhere, probably back with the Bohr equation. Oh, by the way, I would point out, if I had more room, I would have used that third equation to the right of that second equation. This is a great way to keep organized when you have multiple equations that you're using. So we had our primary equation, lambda nu is equal to c. We're missing nu, so our secondary equation, delta E is equal to h nu. We solved for nu. We're missing E, so I would have set up that Bohr equation to the right of that energy equation, so that when I was done, I would take that from the far right, plug it into the next guy from the right, plug that into the next guy from the right, so I'm essentially moving to the left. And so that always keeps me organized when I have multiple equations. So your primary equation, secondary equation to the right of that, a tertiary equation to the right of that. If you had a fourth equation to the right of that, a fifth equation would be the right of that. Keep that in mind if you have physics coming up, because you're going to have a lot of instances where you might have 3, 4, maybe 5 or more equations. That's a good way to keep organized when you're dealing with all those equations. Okay, now we've actually already been introduced to the principal quantum number, and that was n. And remember, that was describing the size of the shell that the electrons were allowed to travel in. So we have 3 principal quantum numbers. Actually, there's 4. We'll talk about the 4th in a little bit. So again, the first one, n, was essentially the size of the shell. And so here we can see where n equals 1, n equals 2, and n equals 3. We're getting bigger and bigger and bigger. Now that s in 1s, 2s, and 3s is the letter that we use to describe the subshell. Now the subshell actually is describing the shape of the paths that the electrons travel in. That's what that L stands for, or is representing. That L is the angular quantum number, and this represents the subshell. So within a principal shell, we may have multiple subshells. We might just have one, but there might be 2 or 3 or more. So again, N is your principal shell. How far are you from the nucleus? So essentially this describes the shape of the subshell, or excuse me, the shape of the orbital. Excuse me, not the shape. The size of your orbitals. Then L, the angular quantum number, describes the shape of your orbitals. Now we're told there's a relationship between L and N, where L goes from 0 up to N minus 1. We'll talk about that more later. Let's get back to talking about these shapes. And so here are the 4 subshells, where we have the S, which is that nice, easy spherical shape. We see the 1s, the 2s, the 3s's, they're getting bigger, going from one principal shell to another. And then we have the P's. Now these are all in the same size. So we're not talking about different sizes, we're talking about different orientations. Note they all have a figure 8 type shape. One's in the x-axis, one on the y-axis, and one on the z-axis. And this allows these electrons to keep away from each other so that we can maximize the greater amount of electrons in the smallest amount of space. So if we're tempted to think that all the electrons are going around the atom in these nice spherical orbitals like we might think about the planets going around the sun, that's not really the way that this happens. We actually, to maximize these electrons in the smallest amount of space, they're going to be found taking up these bizarre paths, where these paths allow them to keep away from one another. And so again, with the P's, we see one in the x, one in the y, and one in the z direction, and that allows them to keep from bumping into each other. Okay, note there are 3 orbitals for the P's, only 1 orbital for the s, and for the d's we have 5, and for the f's we have 7. Now, we are going to have to get to bigger atoms before, maybe say bigger shells before we can fit in the P's, bigger yet before we can fit in the D's, and bigger yet before we can finally fit in the F's. Now note how a d orbital looks like 2 figure 8s in a 1, and most of those f orbitals look like 4 figure 8s in 1 Earth. Now we're going to talk about the energy associated with these orbitals, and so I hope we can see a nice easy path with those s's. Imagine going around a go-kart in that spherical shape, essentially very easy. Then let's think about going around a go-kart track where you have a figure 8 you're traveling in. That's going to take a little more energy out of you. What if we're going to do it where there's 2 figure 8s in 1? Well, that's going to take a lot more energy yet. And imagine that we're in a flying go-kart so we can move in 3 dimensions, and now we have 4 figure 8s to travel in. That's going to take a tremendous amount more energy. So I hope we can see that the s's would have the least, the p's a little bit more, the d's quite a bit more, and the s more yet. And I would also point out again, how many s orbitals? 1 s orbital will be found in an s subshell. How many p orbitals? 3 p orbitals will be found in a p subshell. How many d orbitals in a d subshell? 5. And how many f orbitals in an f subshell? 7. Now let's break out our periodic table, and the periodic table has this shape that it does due to these different subshells. Now in a little bit I'm going to tell you that each orbital can hold a maximum of 2 electrons. So if I have one orbital, like the s has 1 orbital, that's 1 orbital at 2 electrons, so 2 total electrons. Now note that left shoulder is 2 elements wide, representing those 2 electrons. So you might want to take your periodic table and label that left shoulder as the s block. Then, what about the p orbitals? Well, 3 orbitals in the p subshell, 2 electrons per orbital, that's 6 electrons that would make up a p subshell. And note the right shoulder is 6 elements wide, so let's mark the right shoulder as the p block. Okay, where are those d subshells? Well, the d subshell has 5 orbitals, so how many electrons would that be? 5 times 2 for 10. Where do we find 10 elements wide? And that would be the transition elements in the middle. 10 electrons wide, representing the 10 electrons in the d subshell. And then the f orbitals, there are 7 of them in the f subshell. 7 times 2 for 14 electrons, and that would be the guys at the very bottom. So let's label those inner transition elements as the f block. So the left shoulder, the s, the right shoulder, the p, the guys in the middle, which is known as the transition elements, are the d, and the inner transition elements, the guys at the bottom, are the f's. And now we know why the periodic table has this bizarre shape. Now, this information is going to help you a lot, so remember where the S's, P's, D's, and F's are. Okay, now as an example, and back to that relationship between L and N, where L has values from 0 up to N equals 1. So for example, when N equals 3, then L, our angular quantum number, our subshell, can either have a value of 0, 1, or 2. So there are 3 subshells that can fit into the third principal shell. We're going to find that when L equals 0, we have an S subshell. When L is equal to 1, we have a P subshell. When L is equal to 2, we would have a D subshell. And if we ever get up to where L equals 3, then we have an F subshell. And we just learned where the S's, P's, D's, and F's are. Now that third quantum number, m sub L, actually describes an individual orbital. Now, we essentially have values of m sub L ranging from negative L through and including 0 out to positive L. So as an example, when L is equal to 2, so we're talking about a D subshell, then m sub L is equal to negative 2, negative 1, 0, positive 1, and positive 2, for a total of 5 orbitals, or 10 electrons, and again we now know where the D subshell is, with its 5 orbitals and 10 electrons. So again, N represents the principal shell, which is essentially describing the size of the orbitals. L is the subshell, which represents the shape of the orbitals. And then m sub L describes the individual orbitals. Now real quickly I would point out that electrons make up orbitals, orbitals make up subshells, and subshells make up principal shells, so there's somewhat a hierarchy here. So again, electrons make up orbitals, orbitals make up subshells, and subshells make up principal shells. Now do note that all 3 quantum numbers describe a single orbital. So for example, when n equals 2, L equals 1, and m sub L equals 0, well, that says that we have principal shell 2, that's what n equals 2 says. The angular quantum number of 1 says we have a P subshell, and m sub L equals 0 describes one of those 3 subshells. In another example, if we have 2s, so we have the 2s subshell, then our principal quantum number is equal to 2. For s's, L was equal to 0, and m sub L would go from negative L out to positive L, including 0, and hence 0. So we only have 1 orbital in the s subshell. And a 2p subshell, n is equal to 2, L is equal to 1. Remember, L is equal to 1 for the p's. And now m sub L, our individual orbitals, go from negative L through 0 to positive L for negative 1, 0, and positive 1, representing the 3 orbitals that we have in the p subshell. Now we have a 4th quantum number, and this is the electron spin quantum number, and it has values of plus or minus 1/2. Now I can understand where the plus or minus comes from. That refers to the way that the electron is spinning. Plus would be, say, spinning in clockwise versus negative counterclockwise. Now I would point out that if we had 2 electrons with the same spin quantum number, then they are both spinning in the same direction. If they have different signs, then they're spinning in opposite directions. And it turns out that the reason we can get 2 electrons to fit into any orbital is because they have opposite spin. You may be familiar with moving charged particles produce a magnetic field. And so if I have an electron spinning clockwise, I have magnetic north pointing, let's say, to the left. If I have the electron spinning in the opposite directions, and magnetic north would be in the opposite direction, so to the right. And so these opposite poles essentially help attract the electrons through magnetic properties, and that helps offset some of the repulsion due to like charges. So the repulsion due to like charges is actually a little bit more than the attraction due to magnetism, but the magnetism actually does offset a good deal of that repulsion. Okay, I illustrated earlier that the S subshell, because that nice easy spherical shape, has less energy than the P's, which have less energy than the D's, which have less energy than the F's. So it's helpful to remember that they're going to come in that order. First S's, then P's, then D's, and then F's. And actually, not necessarily all at once. And we'll use the periodic table to help us deal with the fact that they don't come in all at once. And I would also say that when it comes to a given subshell, all the orbitals within a given subshell have the same energy. So all the 2p subshells, the one in the x, the y, and the z direction, all have the same amount of energy. And we would actually put one electron into each of those before we would then come back and start pairing them up. And so again, an orbital can hold a maximum of 2 electrons, where you're going to have opposite spins. And so ultimately that means that no 2 electrons can have the exact same 4 sets of quantum numbers. The first 3 can be the same, but the last one, the spin quantum number, would have to be opposite, one positive and one negative. Okay, let me give you a visual of the electron arrangement. So the electrons building up around your central nucleus. So there's our little nucleus. And first, where does our first electron go? Well, it ends up going into a 1s orbital. 1 meaning the first principal shell, s meaning that nice spherical shape. Now the second electron would then join it, spinning in the opposite direction. The first one spinning clockwise, the other one spinning counterclockwise. Okay, so there's 2 electrons. Now if we look at our periodic table, hydrogen and helium are being represented by this. And by the way, helium belongs right there next to hydrogen over there in the s block when we're talking about electron configurations. Okay, now where's our third electron going to go? Well, let's look for element 3, lithium. That's also in the s block. So our third electron is going to go into another s, the second s. So this is the 2s, the 2 saying it's the second region of space. So essentially the principal shell got a little bit bigger. And then the third electron would, the fourth electron would join it, spinning in the opposite direction. And this is somewhat a visual of beryllium. Now where does my fifth electron go? When we look at element 5, we see it's over there on the right shoulder. So we're now starting a p subshell. This would be the 2p. Now we're going to have 3 orbitals, one in the x, one in the y, and the one in the z direction. I couldn't draw that last one. So you'll have to mentally know there's a third one going in and out of the picture. For a total of 6 electrons. 3 orbitals, 2 electrons each, for a total of 6 electrons. And now we're up to 10 electrons. And this would be a visual representation of neon with those 10 electrons. Now, where does our 11th electron go? Well, let's look at our periodic table, and element 11 is sodium over there in the s block again. So it's time to start another s. Well, we've already exhausted 1s and 2s, so it's time for 3s. And I'll have my 11th electron spinning clockwise and my 12th electron spinning counterclockwise. And there's a visual of magnesium. When I go to my 13th electron, well, this 13th electron is going into another p subshell. So here is the p subshell, or the p orbitals, in that third region of space. So this will be the 3p. And again, there's a third one going in and out of the picture that I really couldn't draw. For another 6 electrons, and now we're up to 18 total electrons. And so this would be a visual of argon. Now it's time for our 19th electron. As we look for our 19th electron, our 19th element, again, that's over there in the s block. So we're starting another spherical subshell. That will be the 4th of these. So this is the 4s. My 20th electron joins us, and this will be a visual of calcium. Okay, now, where does our 21st electron go? Well, scandium, our 21st electron, is starting the D block. Now, note all of that empty space down there in the third shell. Our D actually isn't going out into the fourth shell, it's actually going down into the third shell. Now, why did we do these 3 Ds after the 4s? Because there's actually two things that contribute to the energy of an electron in an atom. One is its size. How far is the electron from the nucleus? And that makes a lot of sense. Further from the nucleus, more energy. But the other is due to the shape. Remember, that spherical shape has a lot less energy than that figure 8 shape that we have with the Ds. And so it turned out that the Ds just had so much more energy that it was easier to go out to a larger shell with a nice spherical shape than it was to continue back down there in the third shell with that more energetic shape. Okay, now this one orbital is actually going to represent all 5, and so imagine that there's 10 orbitals that have been shown, that have essentially been drawn in there. So 5 more orbitals for 10 more electrons, getting us to element 30. My 31st electron, gallium, starting another P subshell, and this will be my 4p, so I'm going to continue in that 4th region of space. Now note that by having these bizarre shapes, we've managed to maximize the greater amount of electrons in the smallest region of space. And so that's ultimately why electrons are not all in these nice spherical orbitals, because if they were, then we would have tremendously huge atoms. And instead they want to be much more efficient with the way they pack these electrons. Okay, on to the electron capacities based on the principal shell, the subshells, and the individual orbitals. Now, mathematically, for principal shell, where again your principal shell is based on the, or should I say principal quantum number, principal shell, tells us how far we are from the nucleus. And it does turn out that you have the same number of subshells as you would have number of principal shells. So we find that actually in shell 1, we were so small we could only fit the S subshell. Let's go back here to our picture. When we're in equals 1, our atom was so small that we could only fit in the S subshell. When we get to n equals 2, well, now we're big enough that we can get in 2 subshells, both the S's and the P's. When we got to 3, then we're big enough that we got the S's and P's. Remember, we eventually also got those D's. And then in n equals 4, we would eventually also get to the F subshell. So S's, P's, D's, and F's. Okay, so again, in each principal shell, based on this principal shell number, there's going to be the maximum number of subshells. So n equals 1, 1 subshell. N equals 2, 2 subshells. N equals 3, we can now hold 3. N equals 4, we could now hold 4. Now theoretically, when n equals 5, we could have 5, but now we're talking about atoms that are way larger than any that we have in nature. Okay, now when it comes to the angular quantum number L, this essentially contains 2 times L plus 1 orbitals, because remember that 1 would be the when you would have 0. So essentially think of L equals 1, then we would have negative 1, positive 1, so that's where you would have twice that 1, and then the plus 1 refers to the 0 in the middle. This quickly allows us to calculate the number of subshells, orbitals within each of these subshells. So here we see an example where we have the S subshell, L equal to 0, and so we have 1 orbital, twice 0 plus 1 for 1. When we have the P subshell, L is equal to 1, and so we have 3 orbitals, twice 1 plus 1 for 3. For a D, L is equal to 2, so we have twice 2 plus 1 for 5 orbitals. And for the F's, then L is equal to 3, and so twice 3 plus 1 says 7 orbitals. And we also saw that each orbital can hold a maximum of 2 electrons. Okay, now the relationship between electrons and the principal shell is the number of electrons is equal to 2n squared. So twice your principal quantum number squared. So as an example, when n equals 4, we have a maximum capacity of twice 4 squared, or 2 times 16 for 32 electrons. Now for the number of electrons within a subshell, it would have twice 2L plus 1. Remember, L is equal to your angular quantum number. So as an example, in the D subshell, where L is equal to 2, we would have 2 times twice 2 plus 1, or 10 electrons. We know there's 5 orbitals. That's what the 2L plus 1 would give us if L is equal to 2, and 2 electrons per orbital. Now, I went over earlier where we can find the S's, P's, D's, and F's, and that there were 2 electrons per orbital, and so we could work backwards from that to determine how many orbitals are there in an F subshell if we forgot this equation, because we could go to the F's and see that there's 14 electrons wide, divide that by 2 to get 7 orbitals. So again, a lot of this information, if we forget it, comes from the periodic table. Or we can look at the periodic table to see the application of these mathematic relationships. So don't get bogged down with the math. It's nice to see these math relationships, but we can also rely on the periodic table to answer a lot of our questions. Okay, let's practice some of the things that we've just learned. First, what is the wavelength of a photon with a frequency of 273.1 gigahertz? Okay, we only have one equation that gives us wavelength. Lambda nu is equal to c, and we're after lambda, the wavelength. So lambda is equal to c divided by nu. Now, a gigahertz would be what? 10 to the 9th hertz, or 10 to the 9th reciprocal seconds. So here's the speed of light. Here is that frequency. Again, 273.1 gigahertz, 273.1 times 10 to the 9th reciprocal seconds. Note how reciprocal seconds cancel to give us the appropriate unit of meters. Now when I first look at this is actually very short compared to many of the other wavelengths. Well, we can have long and short wavelength. We can actually have wavelengths in kilometers. It would just have a very small frequency and very low energy. So while this is a lot smaller than the other wavelengths, that doesn't necessarily mean that this answer is wrong. Okay, we're asked to calculate the energy from the ultraviolet line, and it's nice if you're told this is ultraviolet, infrared, radio waves, give you an idea as to what those wavelengths and frequencies should be. Okay, we're asked to calculate the energy of the ultraviolet line in the mercury spectrum, where the wavelength is 403.8 nanometers, and we're asked specifically for the units of kilojoules per mole. Well, first we're going to calculate the energy in joules per photon, and then we'll convert that to kilojoules per mole. Okay, calculate the energy. Well, E equals h nu. We don't have nu, we have lambda, so we calculate nu from lambda. Nu is equal to the speed of light divided by lambda. Speed of light, that constant, 2.998 times 10 to the 8th meters per second. Lambda, and again, we have to make sure it's in meters, so convert those nanometers into meters. And note how the meters cancel to give us the appropriate unit of reciprocal seconds. And now that I have the frequency, I have everything that I need. Again, Planck's constant is a constant. You will be given this on your exam. And you have access to it while you're doing your homeworks. And note how the reciprocal seconds cancels with the seconds in joule seconds. And again, Planck's constant I really wish was joule seconds per photon, because that really is the units that we get when we're done. Joules per photon. to get that energy in kilojoules per mole of photons. Step 1 equals kilojoules per mole. Step 2, start with that just calculated, 4.919 times 10 to the negative 19 joules per photon. And I hope at this point it's all downhill. Step 3, out of joules, can we go to kilojoules? Most certainly. Out of photons, can we go to moles of photons? Again, these should be easy answers. Scratch out the joules, scratch out the photons, circle the kilojoules per mole, just to make sure that it stands out that we got the correct answer. That's a very good habit to get in. Scratch out the units to cancel, circle what's left, just in case you made a mistake. And often we make simple mistakes. This would catch it for you. And when I come up with the answer of 296.3 kilojoules per mole, yes, that does make sense. And the range of hundreds of kilojoules matches the wavelengths of hundreds of nanometers. And note, shorter wavelengths would correlate to higher energies. Because shorter wavelengths correlate to higher frequencies, which correlate to higher energies. Okay, what's the wavelength of light is absorbed when a hydrogen electron moves from the ground state to the third principal shell? Well, the electron is being absorbed this time. So the electron is being excited by absorbing this electron, and this is essentially part of the light that we witness. Things are colored by either emitting wavelengths of certain wavelengths, or photons of certain wavelengths, or are absorbing photons of certain wavelengths and hence taking them out of the visible spectrum. Okay, well anyway, to the problem, what wavelength? We only have one equation with wavelength. Lambda nu is equal to c. Solving for lambda, we have c over nu. And then delta E is equal to h nu, our energy equation, where nu is equal to delta E divided by Planck's constant h. And now we're going to calculate our energy from Border's equation, where delta E is equal to the negative Rydberg equation, Rydberg constant, and you'll be given that constant, times 1 over n high squared minus 1 over n low squared, where n high is 3, and low, well, the ground state is 1. And this gives us 1.938 times 10 to the negative 18 joules that was absorbed. And then again, that would say this is the energy difference between those two allowed states, or those two principal shells. Okay, plugging in this energy, dividing it by Planck's constant. Note how the units of joules cancel, leaving us with the appropriate units of reciprocal seconds. And when I plug this into my original equation, the speed of light, again that 2.998 times 10 to the 8th meters per second, divided by this just calculated 2.925 times 10 to the 15th reciprocal seconds. Note how the two reciprocal seconds cancel to leave us with the appropriate unit of meters at 1.024 times 10 to the negative 7th meters, which is a reasonable answer. 1.02 times to 102.4 nanometers, again in the range of hundreds of nanometers. This is going to be a pretty short wavelength now. Okay, what is the possible values of m sub L for the S subshell? Again, m sub L is your orbital quantum number. Well, remember For the s subshell, L is equal to 0, and m sub L goes from negative L through 0 to positive L. In other words, we only have one value for the s subshell, representing the only s orbital with a value of 0. Now for the p subshell, L is equal to 1, and so m sub L goes from negative 1 through 0 out to positive 1 for 3 p orbitals, negative 1, 0, and positive 1. And the d subshell, well, what is L for d? 2. So we go from negative 2 out to positive 2, including 0. And here are the 5 orbitals for the d subshell. And for the f subshell, L is equal to 3. So negative 3 through 0 out to positive 3. And here are the 7 quantum numbers representing the 7 orbitals for the f subshell. Now we're after the possible orbital values, m sub L, for all sublevels or subshells where n is equal to 2. Okay, well, if n is equal to 2, then L can be 0 or 1. When L equals 0, then we really only have 0 for that angular, orbital quantum number. When n is equal to 1, then we have negative 1 through 0 to positive 1 for negative 1, 0, and positive 1 for those p orbitals. Okay, state the total capacity for electrons in n equals 4. Okay, well, the equation that relates the number of electrons to n is number of electrons is equal to 2n squared. N is equal to 4, so twice 4 squared, or twice 16, for 32. Now, in the fourth shell, we have what subshells? S's, P's, D's, and F's. So for the S's, we would have 1 orbital, 2 electrons. For the P's, 3 orbitals, 6 electrons. The D's have 5 orbitals for 10 electrons, and the F's have 7 orbitals for 14 electrons. So we could have used that information to tell us 32 electrons. Okay, what about a 3s subshell? Okay, well, the number of electrons is equal to 2 times the angular quantum number plus 1. The angular quantum number for an s subshell is 0, so twice 0 plus 1 for 2. What about a d subshell? And do note in the previous problem, it didn't matter if it was the 3s, the 1s, the 5s. They would all have a max of 2. 2 electrons per orbital. 2 electrons per subshell if you only have 1 orbital. Okay, for the d subshell, well, now L is equal to, okay, well, first one is 0, so that's S, then P is 1, D is 3, so twice, excuse me, I jumped over 2. S is 0, P is 1, D is 2, F is 3, so angular quantum number is equal to 2, twice 2 plus 1. For 10 electrons. Okay, I've got a mistake in here. It's actually supposed to be twice 2 times L. So let's go back to that original equation. Number of electrons equal to 2 times, and then in parentheses 2L plus 1. Pardon me for that mistake. So again, the number of electrons based on your subshell is equal to twice 2L plus 1. Your number of orbitals is 2L plus 1. I lost my 2 there. And the p orbital Well, any orbital, doesn't matter what orbital, holds a maximum of 2 electrons. Okay, that concludes this lecture where we were introduced to electron configurations, and we began by being introduced to light and the wave nature. That's where lambda nu is equal to c, and the particle nature, which is where energy shows up, E is equal to h nu. We looked at the atomic spectra and how they were unique for different elements because different elements have different energies associated with their allowed electron transitions. And we saw that for the simple hydrogen atom, that the allowed electron transitions, because they're always going to be in the s orbital, is going to be equal to the negative Rydberg constant times 1 over n squared. And then we did some manipulation of that to get the change in orbitals, which means the change in energy when the electron changes from orbitals. And we saw 3 primary equations. Again, lambda nu is equal to c for the wave equation for light. Delta E is equal to h nu for the particle equation of light. And delta is equal to negative r sub h times 1 over n high squared minus 1 over n low squared for the energy of an electron transition in an atom, a hydrogen atom. Okay, then we looked more at those different quantum numbers. So we had n, we had l, we had m sub l, and m sub s. And we saw a mathematical relationship between them, but if we forget some of those mathematical relationships, sometimes we can get our answer by using the periodic table, and we learned where the s's, p's, d's, and f's were, and that gives us a lot of the information that we need. The electron arrangement showed us an actual visual of the buildup of electrons around an atom. And then we finished off with how many electrons can go into a given principal quantum number or a given subshell, etc. Okay, and that concludes this lecture.